Hi class. In this lecture video, my plan is to go over a few fundamental concepts and terms in vision research. You'll see some of these ideas and terms in the readings, but I'm hoping that I can add a little bit more depth to these explanations. So here we are going to talk a bit about the idea of visual angle. So how this works in plain language is that the environment is more or less different wavelengths of light that enter our eyes through the lens and are then flipped upside down onto our retina, where the rod and cone cells will activate to one degree or another and send that information into the cortex of the brain, where ultimately it interprets light intensity and color and so forth. Well, one of the things we are able to do with visual information is to determine things like size and or at least relative size and distance of objects, because our eyes send information to the cortex based on the relative angle created by the object. As you can see here in the upper graphic, we see a normal sized cow on the left, and then we see what looks like a tiny cow on the right. Both cows are actually the same size, but are inside the same visual angle, so either our brain has to interpret that a weird tiny cow is really close to us, or that a regular sized cow is actually farther away uh, in order to be in the same visual angle. In the lower graphic, we have two cows that are the same size, but one is closer to us because it's taking up a larger visual angle. In other words, the angle marked by the Greek character theta is larger and takes up more space on the retina, as you can see in the lower graphic. So in this instance, our brain interprets the information that more of an object is taking up our visual angle, so it must therefore be either really big or really close. In this instance, it's not a massive cow because that would also be weird. It's just standing really close to us. But what's really neat about this idea is that the brain more or less does this stuff automatically without us really having to think about it very much, although there are certainly times when our eyes might deceive us. Of course, there are tiny little horses and other oddities, but again, our brain is able to recognize it and decipher the information rather than thinking it's just a large horse that's really far away. One of the things we know, and you'll pick up on this if you've taken some physics and maybe even some anatomy courses, is that there are limits to the light wavelengths that the human eye can see. For example, we can't see radio waves or infrared light on our own, and as far as I know, only Superman has X-ray vision. But all joking aside, what we're looking at here is a concept from the text called spatial frequency. On about page 267 of the text, there is a figure that has all these different bars on it, and they seem to have different concentrations of these white to black bars, with less bars meaning lower frequency and higher numbers of compressed bars meaning more frequency. You can kind of mimic this by keeping all of your fingers on one hand together and then looking at your hand at arm's length. You should be able to see the small darker regions between your fingers, which are basically like the black bars we see in the figure from the text. Well, how well we can detect this effect depends on the visual angle, or how much of the retina space in the back of the eye is covered by what we are seeing. The closer an object gets, the better we can differentiate these high frequency items, but the farther away they get, the more spaced out they have to be in order for us to detect it. As you can see in this slide, the pattern of lines packed together closer to us has to be spaced out more as it gets farther away in order for us to detect it. So the light-dark banding or frequency of an object has to be about 40 of these light-dark cycles per degree of visual angle. And this actually makes sense if you think about it. If you see something really close up, you're seeing something at a really high level of definition, a high level of fineness, because the visual angle is actually really, really small. If you move that object back, and you're going to actually have less ability to see it in the same level of fineness as it moves farther and farther away. Another interesting concept that is worth talking about here is sensory adaptation. Another way to think of this is like tolerance. If we eat spicy foods or drink alcohol regularly, but of course not to excess, then our sensory capabilities become adapted to these experiences and substances, and we become less sensitive to them over time. This can happen in a variety of ways and may be also for several reasons. So, why does our body and mind allow us to get adapted to certain types of sensory information? Well, there's probably a lot of explanations for that, but one simple way to think about this is that if we think of humans from an evolutionary perspective, our goal is first to survive. If we adapt to non-threatening or ordinary stimuli, it might free up our mental energy and senses to be more likely to notice or respond to things that are unusual or threatening. It's also important to think about how this happens. To be certain, each sensory system has different methods of adaptation that should be pretty obvious. For example, in the olfactory system, we can think about how smelly a teenager's bedroom is. It might smell really bad to a parent, for example. Well, the teenager may not be really aware of this because they have been adapted to the smell, and this could have taken place either at the sensory neurons inside their nose or even potentially in the brain itself. If you think about it, a teenager's brain could be turned off to their own smelly room over time, so it might not be their fault. The parent, on the other hand, doesn't go into that room much, so the smell hits them pretty hard and instantly. Anyway, for what it's worth, the visual system can also adapt to certain color palettes or even motion perception, and of course, the auditory system can adapt to certain kinds of noise, just as examples. So taking the visual system as an example of what we're talking about from the previous slide, in a really simple way, we can draw an example from the motion after effect. So if we look at phase one, let's say that each circle represents a component of our visual field. The blue circles represent visual fields that can detect downward movement, and the green ones detect upward movement. And in this phase, we're going to be looking at a stationary photo. Then in phase two, the image begins to move upward, which means that mostly the upward visual fields will be activated. You can kind of see that in phase two as more of the green tinted upward cells are being activated, whereas hardly any of the downward ones might be activated. And after this happens many, many times, then in phase three, we are presented with the same image as phase one in a stationary place, but it will look like it's engaging in downward movement. Why? Because the upward movement activation fields are adapted and therefore less sensitive, whereas the downward fields are still the same sensitivity before and are being activated much more easily. Think for a moment when you're on a ride or watching a film with a lot of movement in one direction, and then after you stop looking at it, you might get the sensation that those things are still moving when they aren't. This is exactly this idea.